Welcome to the frontiers of parameterized complexity. Our speaker of the day is Danil Sagunov from Steklov Institute of Mathematics at St. Petersburg, and he will speak on algorithmic extensions of Dirac theorem. Please, Danil.
Thank you for the introduction. Okay, so today we will speak about finding long cycles and paths in, well, I would say two connected graphs. This is related to above guarantee parameterization. So basically, we are given a graph, we know that there is a cycle of some length, and we want to find a cycle that is slightly longer for some parameter k, and we would like to find it in FPT time, or decide that no such cycle exists. Okay, so this is a joint work with my colleagues from Bergen. Mostly the work was done during my visit to Bergen, and I'm glad about it. Okay, so let me just start with Dirac's theorem, if not everyone is familiar with it here. But if you're familiar, let me remind maybe some algorithmic aspects about it. Okay, so Dirac's theorem states that in any two connected n-vertex graph, there is a simple cycle of length at least 2 delta. Delta here and further means minimum degree of the graph, or if 2 delta is greater than the number of vertices on the graph, there is a Hamiltonian cycle. So I guess most of you know Dirac's theorem in the form when it is spoken about Hamiltonicity. So when you have degrees at least n/2, then you have a Hamiltonian cycle inside the graph. And the proof is not really algorithmic, the original Dirac's proof, but you can force it into algorithm. But we would employ some other proof, not the original. Okay, and what can we say about algorithmic aspects of this theorem? So firstly, this cycle can be found in polynomial time using this, the original proof, or the other proofs. And also, if you try to increase connectivity in this theorem, you wouldn't obtain any bound greater than 2 delta. So we will see that there are graphs of arbitrarily large connectivity that do not have cycle longer than 2 delta. And also, if you try to algorithmically find a longer cycle, I mean longer, you have the constant with delta greater, you cannot do it, so it is NP hard. Or even if you add some small function of delta, I mean delta raised to the power epsilon, you cannot do anything about it. It is NP hard. Okay, and the threat of the theorem, which we actually require in our work, so we cannot do it without this theorem also. It is a result of Erdős and Galai, and it says that in any two connected graph, there is an ST path, the path between an arbitrary pair of vertices of length at least minimum degree of the graph. Good. So, any questions so far? You can raise your hand or ask in the chat. I can see the chat. Good. But in order to formulate the theorem, the problem that we will be working with, we would like to see another work by Janssen, Kozma, and Nederlof. It is also related to Dirac's theorem, but in some other way. So if we have a graph that almost satisfies the Dirac's property for the version of Dirac's theorem that I stated the second, yeah, when you have all degrees at least n/2. And now the first, so you can see here, sorry. So the first one is a generalization of when you have at most k vertices that doesn't satisfy the condition of Dirac's theorem. And the second version is when all vertices have a small gap between n/2 and their degree. And the authors proved that both these problems can be solved in FPT time, in single exponential time. And you can see the constants here. Yeah, and they conjecture that combining these two properties, I mean that you have k vertices with very bad degree and all other vertices have a small gap between the needed degree. Then this problem also can be solved in single exponential FPT time. And we would like to formulate our problem about a cycle above Dirac's guarantee in such a way that we will capture this conjecture. And so we will answer it positively. So we can, in fact, generalize Dirac's theorem. And we can call it Dirac's theorem with bad vertices, for example. So basically, you can pick in a two connected graphs any set of vertices. Here we will call it B. And you can remove it from the graph and consider the minimum degree of the obtained graph. And then you have a guarantee that you have a cycle of length at least 2 times the minimum degree of the obtained graph, or you see, or a graph that uses all the vertices in the obtained graph. Okay, so this is a generalization. You can see that it captures the conjecture because, well, you can select B equal to these bad vertices with bad degree. Then you know that their number is at most k. So removing them from the graph will decrease the degrees of all other vertices only by k. So in the graph G with deleted B, you will have the minimum degree n/2 minus 2k. Yeah. And so you would like to find the cycle above this. So you would like to find the cycle plus 2k over this guarantee. Oh, sorry, plus 4k. Yeah. Okay, so I guess we're now ready to formulate our problem. And it is based on this guarantee that okay, there is a question. So the outcome of the theorem is that there is a cycle of length at most n minus b, because at least n minus b, right? Because it is, so it's not Hamiltonian. Yeah, it's not Hamiltonian. So in fact, in our work, there is some case when you are left with cycle that passes through all vertices that are not bad. And then we have some routine that inserts these vertices from B inside the cycle, right? And this requires also single exponential FPT time. Okay, did I answer the question? Did I understand it correctly? Okay, thank you for the question. Yeah, so this doesn't give us Hamiltonian cycle. Okay, so our problems, our two problems are like this. So first is long Dirac cycle. Okay, so we're given a graph and the set of best vertices, and we would like to find whether there is a cycle of length, at least the guarantee that we saw earlier on the previous slide, plus the parameter k. And of course, our parameter here is not just k, but k plus b, because in some way b decreases when you delete b, you decrease the degrees of all vertices. But in fact, I'm not sure that you cannot handle it without b. So probably we can state it as a conjecture that could we avoid b in the parameter, make it dependent only on k. And we do not know anything about this as far as I understand. Okay, so what is good behind this problem? So it captures the conjecture. Also you can see that this is always yes for k equal to 0, as it always happens for above guarantee parameterizations. And the second problem is based on the Erdogan theorem with bad vertices. And it is formulated in the same way. Parameter also is k plus the size of b. Okay. Any questions so far? Feel free to ask. Good. So let us start with some simple question. So simple question, how can we approach such a problem? We would like to solve it for very, very small k. So we know that, okay, so you can see now my pointer. Okay, we know that it is always yes when k equal to 0. So what can we do? We can try to solve it for k equal to 1. Okay, let's try to do this, but not for long Dirac cycle, but for long Dirac path. So you can formulate long Dirac paths in the same way. Just replace the cycle with path, and it's all. Okay, so let's try to solve long Dirac path for k equal to 1. And also we will consider that there are no bad vertices, just for the sake of warm-up. Okay, so we would like to find the path of length to delta plus 1, or decide that no such path exists. Okay, so we find a long cycle using the Dirac's theorem proof, and we can be certain that the cycle we found is of length at least to delta, because if it is longer, we obtain that the given instance is a yes instance. Okay, then what can we have outside this cycle? As well, we can decide if this is a Hamiltonian cycle, then it is also clear that the given instance is a null instance. Okay, so suppose we have an edge outside the cycle. Then, since the graph is connected, we should have a path connecting this edge with the cycle. But then this clearly yields us a path of length at least to delta plus 1, because you can start with this edge and gather to delta minus 1 edges of the cycle. Okay, so now we can be sure that outside the cycle there are only isolated vertices. I mean, all vertices are connected to the cycle, hence the cycle is a vertex cover of the graph. Okay, so assume we have a vertex, and then assume that we have 2 consecutive neighbors of the cycle for this vertex. But then it is clear that we can enlarge the cycle, and again we obtain that our instance is a yes instance. Because, well, why this is a yes instance? When we obtain a cycle of length to delta plus 1, we just pick some vertex outside. We know that it is connected by an edge, and we gather to delta minus 1 edges of the cycle. Okay. So we know that there are no consecutive neighbors, but we know that its degree is at least delta, and all its neighbors is on the cycle. Then this vertex is adjacent to neighbors over 1. Yeah, so it is adjacent to either even vertices of the cycle or odd vertices of the cycle. And this holds for each isolated vertex. Otherwise, we clear can decide whether it is yes instance or a no instance. Okay, so assume that there is a vertex, other isolated vertex, that is connected to vertices with other parity. So it goes like this. We have some other isolated vertex connected like this. Then we can trivially enlarge our cycle by two vertices like this. Okay, and decide that it is a yes instance. So if we cannot do this, then we are sure that all vertices outside the cycle have the same neighborhood. All right. Then we need the last observation to see that it becomes really that it becomes a graph with really easy structure. So assume there is an edge that goes between non-neighbors of the isolated vertices. But then we can again enlarge the cycle, and it goes like this. Yeah, so we can take isolated vertex into the cycle. So we enlarge the cycle if there is any edge. So we can be sure that these vertices that are not neighbors are independent set. So the vertex cover of the graph. I forgot to say that we call these vertices one-on-one neighbors because, well, they are between the neighbors. And a half of the cycle forms a vertex cover. Okay, so now we know that the vertex cover of the graph is of size exactly delta. But we know that the bound on the longest cycle of the graph is exactly 2 times vertex cover, because each edge should be incident to a vertex of the vertex cover. Okay, so we obtain that if we come to this, then there is no path of length to delta plus 1, because there is no cycle of length to delta plus 1, and all vertices are isolated outside. Okay, yes, and we obtain a vertex cover. Yeah, so what we proved now is that in a two-connected graph, there is no path of length to delta plus 1 if and only if vertex cover of this graph is equal to the minimum degree, and that cannot be less. And here we also see that large connectivity does not help because, well, we have a vertex cover, and each vertex outside is connected to all vertices of the vertex cover. Hence, this graph is delta connected. But the longer cycle here is exactly to delta. No. These vertices are not of degree 2. Yeah. So what you have here that these vertices that are independent, they have the same neighborhood as isolated vertices. So basically, vertices of this type are adjacent to all vertices in the vertex cover. Yeah, so they can be seen as independent vertices. Great. Okay, sorry, I will erase this. All right. Okay, we've seen some facts, and we've seen technique with isolated vertices that will help us further. Okay, and we can also show that this theorem is not true for cycles, because we have graphs with arbitrarily large vertex cover, but we do not have a cycle longer than to delta here. And this graph looks like this, an example of this. And this is also some beautiful structure that we will generalize later. So this graph doesn't have a cycle of length to delta plus 1, but a vertex cover of this graph is quite large. because we have many clicks here. Great. Okay. Let's go further to the more complicated cases. And what do we need to note is that paths are easier to find than cycles. What do I mean is that if we solve long Dirac cycle, we solve long Dirac path. And the construction is really simple. If we want to solve long Dirac path, we just take our graph and add an universal vertex to it. Yeah. And then if we had a long path, it becomes a long cycle. And to the other direction, if we had a cycle, we also can remove the universal vertex and obtain a path. Yeah, and because addition of a universal vertex increases the degree, we have larger guarantee. So when removed one vertex, guarantee decreases, and that's all right because in initial graph the guarantee was less. Okay, if there is any question, feel free to ask again. Okay, so now if we solved long Dirac cycle on two connected graphs, then we solve long Dirac path on, here is misplaced long Dirac path and long Dirac cycle. Yeah, we need to switch them. So because of addition of universal vertex, you make a connected graph, two connected. So for Dirac path, we can solve it on one connected graph. Good. Okay, let's go further. Now that we know that we can solve only cycles. Okay, and the crucial, the crucial result that we rely on it is like we take the proof of log. Well, you can find this proof on the web. It is harder to find it in some paper. And based on this proof, well, we change it a little bit, adjust it for our purposes. And then if we cannot enlarge our cycle using path outside the cycle, we obtain a really good structure that we then solve in different ways depending on what structure we have obtained. Okay, so we will proceed with the proof similar to Locke's proof, but we'll adjust it to our purposes. And you can see the basic idea of how it's done. And let me also mention that we ignore bad vertices now. So we consider only that there are no bad vertices. The set of bad vertices is empty because, well, it would take many time to consider these bad vertices, to contract edges, but ideas are almost the same, just more technicalities with bad vertices. Okay, it just looks better when there are no bad vertices. Okay, so what can lie outside our cycle? What that we want to enlarge? So that can be isolated vertex or an edge, or a separable graph. What do I mean here is that it is connected, but not two connected, or just a two connected graph. Okay, and we need to consider these cases separately. For isolated vertices, we briefly considered how it is done. We need to see the neighbors inside, and I will not focus on isolated vertices much here because, well, it is not much different because the length of the cycle is close to 2 delta. But let me focus on the very simple case, the case of an edge. Well, it appears that if we have an edge outside the cycle, then we can always enlarge it. Okay, here we need a little remark that you can see here that the length of the cycle is 2 delta plus p. Yeah, and we consider that P is less than some constant times delta? Well, because if we obtained a cycle larger than P, well, larger than some constant over delta, then we know that our parameter that was given initially is also at least some constant times delta. But then we can just use color coding because K is not much smaller than delta, and to delta plus K, well, just increases this constant. So we just increase K by some constant number, and that's all right. So we consider that P is smaller than some constant over delta, because if we found a cycle that is long, it is all right. Okay, so let us proceed with the edges. So of course, if we have such a picture, so endpoints of an edge have two consecutive neighbors, then we can enlarge cycle like this, and this is all right. If this picture happens, we also enlarge our cycle by one edge. So now we know that the distance between a neighbor of U and a neighbor of V is at least 3 on the cycle. Well, U and V here are the endpoints of the edge. Okay, so denote by S the common neighbors of the endpoints, and by T all the set of all neighbors on the cycle. Yeah, of course, we consider that U and V are outside T. Then we know that the length of the cycle is at least 2T, because, well, if you have consecutive neighbors, you can insert either one vertex or an edge. Yeah, this picture, if you have consecutive neighbors. And plus S, because you see each common neighbor of U and V, it says that the arc that goes, the arc with endpoint from S should be of length at least 3. Hence, each vertex from S increases this arc of length 2 by at least 1. Yeah, so the length of the cycle is at least 2T plus S. Okay, and now we need to do some arithmetic and consider two cases. Either vertices have delta minus 1 common neighbors or less than this number. Okay, if this is at least delta minus 1, then the length of the cycle is at least 3s, because T is at least S. Yeah, and this is much greater than 2 delta plus P, because P is smaller than delta. And when S is smaller than delta minus 1, then we can do this. Just an inclusion-exclusion principle, because T, the size of T is equal to the sum of NU and NV minus S. And we obtain that since the neighborhoods of U and V are at least delta minus 1, yeah, here neighborhoods are inside the cycle. This is also at least 3 times delta minus 1. This is also at least 2 delta plus P. Hence, we obtain, if we cannot just insert an edge inside our cycle, the cycle is already very, very long. Yeah, so it is at least, well, it is approximately 3 delta if we cannot insert an edge. Yeah, is it okay? Any question? Okay, so edges are simple. So we now can be sure that if we encountered an edge, it is really simple. We can enlarge our cycle, or it is already long. So now we are left with 3 structures: isolated, separable, and 2 connected. Okay, let me consider 2 connected graphs. Well, considering separable graphs is really similar to considering 2 connected graphs, because, well, inside the separable graph we have leaf blocks that are also two connected, and their degree is also close to that of just two connected graph, because they are connected only by one vertex to such a separable component. So we will consider just two connected graphs. Okay, so assume you have a two connected component, and we will do some arithmetics here also. So take two vertices that have the most number of neighbors in C. And what do we want to do? We want to find the longest path between H1 and H2. I mean, the longest path that we can find in polynomial time, and try to insert it into our cycle. Okay, so let's see what are the properties of cycle if we cannot do this. Okay, so take the two vertices with the most number of neighbors in cycle, and if let H1 have n1 neighbors inside the cycle, then we know that the minimum degree of H is the minimum degree of G minus n1. Okay, so this gives us a long path. I mean, long is delta minus n1. So we know that this red path is at least delta minus n1 just because of the Erdogan theorem that we discussed earlier. Yeah, so now we know that these arcs should be of length at least delta minus n1 plus 2. I mean, the arcs between a neighbor of H1 and the neighbor of H2. Yeah, because we would like that we do not insert this path and enlarge our cycle. Yeah, so again, we need to do some arithmetics, and it goes basically in the same way as for an H. And so we denote the sets of common neighbors and the set of all neighbors. And the bound again is to T, but now the path between H1 and H2 is really long. It is delta minus 1. So each common neighbor adds delta minus 1 to the length of the cycle. And from this, we can consider several cases, and we can see that n1, the number of neighbors of H1, should be less than delta over 2. Or we can insert the path, or the cycle is already long. So now we know that the n1 is less than delta over 2. So now we'd like to formulate another assumption and find a contradiction. So I mean, enlarge our cycle. So assume that there is a matching between H and C of size at least 3. Yeah, so it goes like this. So we have some other vertex H3. And we should have at least 3 arcs of length at least delta minus n1 plus 2. Well, because there are 3 arcs that are provided by this matching. And we should have n1 arcs of length at least 2, just because we have n1 neighbors of some vertex on the cycle. So we have a bound of 2 and 1 for each arc of length at least 2. And then we should have at least 3 arcs of length at least delta minus n plus 2. So this is basically an addition of well, you can see it. And we can say that this is at least 2.5 of delta, just because n1 is less than delta over 2. Okay. So we can see that if we found the matching between a two connected component and the cycle, then it is done. We can enlarge the cycle. So we come to that the matching size between a two connected component and the cycle is exactly 2. It cannot be less because the graph is two connected. And of course, this can be decided in polynomial time. So we know that the path is inside this graph is really, really long because the matching is so small. Yeah. So, and because this path between H1 and H2 is really long, we can only have this picture that the endpoints of the matching, of any matching of size 2 that we take, they should be on opposite sides of the cycle. I mean, the distance between them should be at least delta. So all neighbors on the cycle, they look exactly like this. So we have a small part of the cycle on one side, and on the opposite side, I mean, the lengths of these small paths are at most p in total. Yeah, and cycle is connected to these small parts. Yeah, and okay, so we proved this just for a single component. Then we actually would like to show that such small two parts are connections for every two connected component that we can encounter outside the cycle. Okay, so what do I want to say? So assume that there is other two connected components, and of course, it should also be connected in the same way for some two opposite small parts of the cycle. Yeah, so assume it like this, but these parts are different from the parts of the first two connected component. But then you can see that if the picture is like this, we can obtain a really long cycle, because we can take either this cycle or this cycle. And you see that union of these two cycles, it contains the whole cycle C. Yeah, you can see that if we take green cycle simultaneously, then they will give us the whole cycle. Hence, at least one of these green cycles should contain at least half of the vertices of C. And since these red paths are really long, at least delta minus some constant, we obtain a path of length close to 2 and plus 1 delta, so 3 delta, yeah, because half of the cycle is delta. Yeah, so we cannot have this. So any two connected components should be connected to the same opposite small sides of the cycle. Yeah, so it looks like this. So these blue parts of the cycle is these small parts that each two connected component is connected to. So basically, you can observe it as a separator. If you remove these two parts, you obtain many two connected components. Yeah, and for isolated, for separable components, we can also show that they are connected to these two parts. Well, it's just more technicalities with leaf blocks, since they also two connected, and some cut vertices and so on. But it is also looks in the same way, and they are connected to the same parts. Okay, so now assume that there is a two connected component and an isolated vertex outside the cycle simultaneously. And this is a really crucial part of the proof, that these two structures cannot be simultaneously, or we can enlarge the cycle. Yeah. So assume there is an isolated vertex outside the cycle, and let me draw a bit, because this picture is quite non-representative. I'm sorry for that. Since this vertex, it has many neighbors on the cycle, well, at least half. I mean, and these neighbors should be close to each other, because it is half, but distance between them should be 2. Yeah, so we can always choose this vertex to be really close to this vertex. Yeah, so distance here will be some constant times p. And also this vertex, we can pick really close to this part. It is also some constant times p. And then we can just take this cycle. Yeah, this cycle. Yeah, and we avoid it with this cycle. Just some constant times p vertices. So the length of the cycle is close to 3 delta. It's 3 delta minus constant times p. Okay, so is it clear? Any questions so far? That is basically all parts of the proof that I wanted to discuss with you, because all the main ideas are shown here. So it is very crucial that we cannot have simultaneously two connected and isolated vertices. Okay. Okay, so this was some pictures that aren't needed at all. Okay, so I will clear the. So what we obtain, we have that there are 3 possible structures, and now we know that it is either isolated vertices or 2 connected and separable components. And there is a dichotomy in the sense that we either obtain a vertex cover, as we discussed before, in the same way. It's just more consideration of some bad neighbors. Or we obtain a good structure that we call Dirac decomposition. And I will define what is Dirac decomposition a little bit later. Okay, so any questions so far? It is now a very crucial result of our work, where we obtain either a vertex cover or a Dirac decomposition. Good. So our main structural lemma looks like this. So given a 2 connected graph with with cycle a little longer than 2 delta, we can either enlarge it, find the vertex cover, which size is delta plus constant times parameter, or obtain our structure that we call Dirac decomposition. Well, because it is based on Dirac's theorem. And this is just the sketch of the lemma, because here I consider that there are no bad vertices and missed some other points, but it looks like this. Okay, so we have come to the problem graph of our work. So what is it about? So, okay, the problem that we aim to solve is long Dirac cycle. And then we have seen that there are 2 cases, either vertex cover or some good structure. And for vertex cover, we have this separate part. We have to solve the problem where we have a slightly larger than minimum degree vertex cover. It is delta plus 3p. Or when we have, as I said before, answering the question, or we have to insert vertices from B one by one into some Hamiltonian cycle. Yeah, and this is called almost Hamiltonian Dirac cycle. So when we want to find a cycle that is close to Hamiltonian cycle. And these 2 parts allow us to deal with the vertex cover case. And this part allows us to deal with the case when we obtain the Dirac decomposition. Yeah. Then it is using the structural lemma that we discussed a slide before. We combine it into the algorithm for long Dirac cycle. Okay, and these 2 parts are pretty independent. So you can take our paper that is available on arXiv and just read any part you want. Okay. So let us go further. And I will not speak here about the almost Hamiltonian Dirac cycle and the longest T cycle problem. Yeah, longest T cycle is a very natural problem. It is about that we have just a graph, not too connected or connected, and we want to find just a cycle of length at least k between two given vertices. We will see how this problem comes in handy. Well, you can see the proof in our paper. It is also standalone, so you can see it separately from the other paper. Okay, so coming back to the problem graph, we will now consider the left part, basically the Dirac decomposition. So Dirac decomposition looks like this. We have these two opposite small parts called P1 and P2, and all other parts are either two connected or you can see two connected or separable, and they can consist of only bad vertices. Yeah, because this happens for bad vertices. You cannot have any large path inside such type of components. So they just give us some problems that we need to avoid using some color coding. Yeah, so we cannot say anything about these gray components consisting of only vertices with bad degree, because they can be arbitrary. We cannot have any degree condition there. Yeah, but their number is small, so we can deal with them using color coding. Yeah, and blue parts here are exactly two connected subgraphs of G. Yeah, so blue parts for two connected components is clear. They are just equal to the to this component, and for separable graphs, they equal to their leaf blocks. Yeah, and what is good about these blue parts, which we call Dirac components? Well, the basic property of these parts is that if we want to go through them, then we can only do this once. So if we enter it and walked just one single edge inside this blue component, then, well, we cannot then enter this component at all because of the matching conditions. Yeah, and we can see this in the pictures that go further. Yeah, so yeah, if you have a cycle, then it can only contain one path inside this blue component. It cannot do something more complicated than this, just because of the matching condition. So if you had two paths, then your matching size will be at least 4. Yeah, and very, very crucial lemma here that looks quite clear is that if we really want to find the long cycle, then we should look a cycle that goes through two distinct Dirac components. So it exactly connects in some way these two green paths. They are long, and we need to connect them outside. Yeah. So basically, our algorithm using this lemma would be consider every pair of Dirac components, then find this long green path, and this long green path we find using long Erdős-Galias path, because, well, this is a two-connected graph of large minimum degree, and we want to find a long green path between S and T. And then we would like to connect them outside. And since these green paths are long, these orange paths are enough to be just some constant over k, because we have 2 delta minus constant already using only green paths. So total length constant times k is enough. And then we employ the longest T cycle problem. So you can see it very clear in this picture. So you just introduce S and T to this picture, connect them to the endpoints of these green paths, and just look for a cycle that connects S and T. And this cycle will yield these orange parts that will provide us the connection between green paths. Yeah, and this is basically what we do with Dirac decomposition using the long Erdős-Galai T-path algorithm. So it's just like this. And also, of course, longest T cycle we use. Yeah, but this lemma that is stated in the slide is very, very technical. I mean, to prove it, you need very, very technical ideas. And this mostly happens because of the bad vertices. Because you can find some long paths going through bad vertices and combine them into a long cycle. Okay, but here lemma is clear, I guess. Okay, so now let me just briefly consider the long Erdős-Galai path, and for it, gladly, the basic idea is exactly as for long Dirac cycle, but the algorithm for it is in a way different. So it is not like the algorithm for long Dirac cycle, but the starting point is the same. So we want to find a longest T path of length at least delta plus k. And we again start with summest T path from guarantee. And we want to enlarge it. And we again follow the logs proof for cycles, again adjusted for our purposes. Okay, so isolated vertices outside the path now always allow enlargement because the path is short, it's delta. So we should have two consecutive neighbors. Otherwise, the path is 2 delta. And then following, again, these cases for two connected and separable graphs, we obtain an analogous to Dirac decomposition, so-called Erdős-Galai decomposition. Yeah, so because of the name of the theorem, since it's due to Erdős and Galai. And for this decomposition, we also have nice properties that the matching between blue parts that are called Erdős-Galai components, as you can guess already. And again, we can just enter each part just once and leave it just once. So if you want to find the longest T path, you just should fix a blue component, fix its endpoints, then find the longest path inside this blue component recursively using our algorithm. Then just find a connection between ST and these two endpoints. Yeah, and this is again done using the ST cycle algorithm, which we use as a black box. Okay, so this is quite clear, but analysis of recursion is not really clear. I mean, it is not simple, so it is quite technical. So it is different to the Dirac decomposition. But proof here is not so hard. So the proof is not so hard as was the proof for long Dirac cycle. Okay, but I have no time to go into the details of this. I'm sorry about this. So we just clear all pictures. Yeah, we find longest path recursively and just connect them with longest T cycle. Okay, so maybe any questions so far? I have like 10 minutes left, and I think I have time. I have enough time for the slides left. And okay, let us go back to the problem graph. And I should know that we discussed the left part. Yeah, the part, recall the main structural lemma, it yields us either a vertex cover or a Dirac decomposition. And we already considered the Dirac decomposition. Now we go to the right part of the problem graph. We go to the vertex cover. And okay, so the part with the vertex cover is really related to the work mentioned earlier of Janssen, Kozma, and Nederlof. But we again need to tweak their proof so it would work for our purposes. So in a way, well, quite in more general way. Okay, so we have very small vertex cover. I mean, very small above minimum lower bound, yeah, above minimum degree. So consider the independent set. So any long cycle, it is of length at least 2 delta. So it should contain at least half vertices from the vertex cover. So it contains at least delta vertices of the vertex cover. And the crucial idea here, which will help us to tweak the ideas that were discussed earlier. So it was first introduced by Hagvist, then Janssen, Kozma, and Nederlof tweaked them to work for their problem. Now we tweak it more for work for our more general problem. Okay, and now each vertex outside the cycle have very many neighbors in cycle. So it looks like this. So many neighbors. I mean, the distance between them most of times, I mean, excluding some small number of cases, p number of cases. So they are located on the distance 2, these neighbors of each isolated vertex. And then we can just, if you consider a cycle and consider an isolated vertex, since each of them has so many neighbors inside the cycle, there is always a place for such a vertex that this isolated vertex can stand. Yeah, so consider this blue vertex, and you see it has many neighbors. So it can stand between any 2 neighbors of the vertex cover. So consider such a replacement. So consider these 2 neighbors, and we insert this vertex. Then consider some other vertex. We again can replace it. Sorry about the missing point. Somehow it goes away. Yeah, so again, we see the place for it, and we insert it again. Then again, we see some place. You see that there is only one place, and we insert it here. And we can do this delta minus 3p times, because so many neighbors each vertex has. Yeah. And then, yeah, we force some subset to be in the cycle. And then, since X is really large, at most 2p vertices in S have less than 2p neighbors in X. And we denote this set by Z. This requires some arithmetics. I have no time to speak about this much. So let me just briefly discuss what goes then. So yeah, we have very small set inside the vertex cover, which have really few neighbors inside X. And then using Bondi-Quattle lemma, that was exactly the idea used before, we can reduce our problem to finding a specific path cover of Z, of the set Z. And this is, well, how we prove that such path cover yields us a cycle. Well, clearly that a cycle yields a path cover because we just remove some vertices, I mean, from X here. And a cycle breaks in some number of paths. And how do we prove how to combine such a path cover into a cycle? Well, we use the Bondi-Quattle lemma. And Bondi-Quattle lemma states that if there are 2 vertices which sum of degree is at least n, we can add an edge between them, and this doesn't change the Hamiltonicity of the graph. And here we just consider the graph induced on the vertices of the cycle we look for. And then we can see that this independent set, its degree is really large. It is more than the half of the length of the cycle. So we can obtain a clique here. Yeah. And then since now degree became much larger because we made this a clique, we can now add edges between these vertices, independent vertices inside our cycle, and vertices inside A, because they have at least 2p neighbors inside X, and this is all right. And then the path covering Z helps us to combine this into a cycle, because we have many neighbors that connect vertices outside of Z. Yeah, I know that this is a really brief explanation of what's happening before, but unfortunately I cannot say more. But you can ask any question if you want. I think we have time now for a question at least. Okay, so feel free to ask. Okay, so now I'm clearing the pictures, and then again consider the problem graph. Now we consider every part of the graph. So left part allowed us to deal with longest T cycle, which is a standalone result. Not well, it is a natural problem that is not related really to our work, but it is very helpful for our purposes for dealing with bad vertices. And each other problem we discussed also. So long-Galilean path, it is above guarantee problem, Dirac decomposition. And the right part is for vertex cover, and almost Hamiltonian Dirac cycle is exactly for fitting back vertices, bad vertices inside the Hamiltonian cycle that is and doesn't have any bad vertex on it. Yeah, so let me summarize and give some open questions. So we show that there is a cycle of lengths to delta plus k. Well, we question it. Is there a cycle of lengths to delta plus k? We can decide it in single exponential time in k plus b. And well, we can say it also as an open question that is not mentioned as a point. Can we avoid a linear dependency on b? Maybe it can become logarithmic or polylogarithmic, or avoid it at all. This result generalizes some other rising problems. Well, I can say they are quite natural. Well, also we solve open problem, open conjecture. Then we solve longest cycle that can be considered as a standalone problem. And the open question here is, can we, so this research is some kind of starting point for finding cycles longer than guarantees. Well, not just this research, but this and many papers before that base on finding long cycles above guarantee. So can we solve other above guarantee versions in FPT time, which guarantee proofs related in somehow to Dirac's theorem and Erdogan theorem? For example, cycle above average degree. So there is a guarantee that in a two-connected graph, there is always a cycle of lengths at least average degree. Can we do better than this? Then there are also some guarantees that there is cycle of lengths to delta through some given set of vertices that is small. But if you raise connectivity, then this set can be also increased, can have increased size. And also there are some analogs of Dirac's theorem for directed graphs. Can we do something about directed graphs? Well, I myself believe that it is hard, but well, can we prove the hardness then? Okay, so basically that's all. Thank you for your attention. I'm really glad to give this talk. Yeah, thanks.
Thank you very much, Daniel. So now we can ask questions. Is there any? It's not a question of Bart. It's yes, it's a thanks.
Yeah, thank you, Bart.
But it also looks like there were a lot of questions during the talk, so it looks like.
Yeah, sure.
Yeah. So thank you once again, Danil, and see all of you so next week. Bye.
Yeah, thank you very much. Bye bye.